now that we understand what makes a molecule aromatic, let's talk about the chemistry you can do to an aromatic molecule. This is going to be called electrophilic aromatic substitution reactions. And these are a vital tool for functionalizing aromatic rings and are useful to make complex molecules. In fact, when I was a graduate student and when I was doing chemical synthesis, this was a lot of the chemistry that we did. And at many schools, maybe your own, you'll find that this is your first entry into the concept of chemical synthesis, making bigger molecules from smaller frameworks. These reactions rely on the fact that most aromatic rings are relatively electron rich and therefore can be nucleophilic via a standard addition type reaction. However, as we highlighted earlier, these aromatic rings are super stable. And since they're really stable, it means that they're unreactive. And so we're also going to introduce the concept of a catalyst, where a catalyst allows you to lower the barrier of activation to do chemistry. And so you're able to do a reaction that would not proceed otherwise. Now, the standard reaction is shown here, where what we're able to do is take benzene, which is aromatic, and add some kind of electrophile to the ring here in a new bond formation reaction. I'm going to highlight each of these reactions in just a little bit, but first I want to walk you through the general mechanism. So let's draw here. Again, I've used the general E+ as any good electrophile. So mechanistically, let's work through this. We're going to start with a benzene ring, and here it's going to be totally undecorated. We'll deal with decorations in just a moment. And here's our general electrophile. The way this chemistry will proceed is the ring will serve as a nucleophile and will attack the electrophile. You'll notice that the arrow flows from nucleophile to electrophile, and you'll notice that it has two heads to it because this is a 2-electron process. So the electrons will flow from nucleophile here to electrophile here with 2 heads because it's a 2-electron process. And I will get this resultant product here. Now you'll notice that there's nothing happening at these 2 double bonds. I'll leave them alone. I'm going to add the electrophile here. And I'm going to place the hydrogen atoms as well. And I'm going to add an important charge there. So you'll notice that what we've done is we've added an electrophile, but we've also done something really important. We've disrupted the aromaticity. If I asked you if the nucleophile on the left-hand side was aromatic, you'd say, of course. If I asked you if this was aromatic, you'd have to say no. And so what we need to do is reintroduce aromaticity. And we're going to do so by having some sort of general base around. B with a lone pair for our purposes right now. Now, typically the base is actually the catalyst that activated the electrophile. And so we sort of serve dual purpose here, where the catalyst for activation both makes a better electrophile and becomes a base later. Really smart chemistry. This base here will abstract this hydrogen atom. And then the 2 electrons in this carbon-hydrogen bond will go here to reintroduce aromaticity and make a new carbon electrophile bond. This is the same mechanism for all of the reactions I'm about to show you. Benzene ring attacks the electrophile, and deprotonation leads to formation of the final product. I take something aromatic, disrupt the aromaticity, and then reintroduce. So let's take a look at all of the reactions that you can do using this chemistry. So there are many reactions of aromatic rings, and I've shown them all here. I'm going to go clockwise. First, there's halogenation reactions. Now, adding a halogen is adding an X, remembering that X is the fluorine, chlorine, bromine, and iodine column. Now, most commonly, you're going to see X being Cl or Br, especially Br, just because it's a liquid bromine when we handle it in the lab, and therefore it's the easiest to handle and the one that we do chemistry on most frequently. If I ask you what the catalyst is, the catalyst here is iron trihalide. Typically, X will align with the halogen that you're adding to the ring. So for example, I could add Br2 and FeBr3 as the catalyst. So we can halogenate this aromatic ring. The next reaction we can do is called a nitration reaction, where you add an NO2 group that comes with nitric acid, and the catalyst here is H2SO4. This here is sulfuric acid, and sulfuric acid is a very common strong acid and proton source as a proton catalyst. You're actually going to see it a lot throughout all of organic chemistry. So we're able to nitrate this aromatic ring. Now the nitro group is particularly interesting because it can undergo further chemistry that you're going to see later in this course. But this nitro group can be reduced to an NH2, like so. We're going to see reduction conditions later on, but reduction makes less bonds to an oxygen and more bonds to a hydrogen. Now we can also choose to sulfonate an aromatic ring, shown here, where again you add SO3, and there's that H2SO4 or proton catalyst again. We can also do something called a Friedel-Crafts alkylation. An alkyl group is a carbon chain. So alkyl equals a carbon chain. Most commonly, you will see R as being some sort of like tertiary butyl group or something along those lines, as the tertiary butyl group is a very useful functionality. You can also do a Friedel-Crafts acylation up here. What an acyl group is it is a carbonyl bound to a chain. So an acyl group is like so, where we have some sort of carbon chain there. Now, both the Friedel-Crafts alkylation and acylation have the aluminum trichloride here as the catalyst. And this aluminum trichloride activates both electrophiles. So this is a survey of all the types of chemistry that can be done. And in fact, this is a non-comprehensive list, but it's the comprehensive list that you will need. Halogenations, nitrations, sulfonation, and the Friedel-Crafts reaction. And all of these follow the same general mechanism. The aromatic ring attacks the activated electrophile to form a non-aromatic intermediate. That intermediate has aromaticity reintroduced to give the final product.